Hi everyone. Thanks for attending Manufacturing Automation's webinar on testing emergency stop systems. This is our very first webinar and we are delighted you have all taken the time to learn more about this very important safety topic. I'm Elisa Dalton, the editor of Manufacturing Automation, and I'm also the moderator for this session. Joining me today is our speaker, Doug Nix, Managing Director and Principal Consultant at Compliance Insight Consulting. Before we begin, we have a couple of housekeeping items to take care of first. We're going to be asking some poll questions throughout the webinar, and we really encourage you to participate so we can better understand your experience and we can tailor the presentation to be more relevant to you. Questions are welcomed at any time. You can submit them using the dialog box at the bottom of your control panel, and we'll take them as they come in. Following the Q&A, there's also going to be a very short survey that we ask you to please fill out. We promise you that we will take all feedback very seriously, and we will use this information to help us design better webinars for you moving forward. And within the next week, the presentation will be archived on our website, so keep an eye out for a thank you email from us containing that link, as well as a PDF with additional notes. Feel free to share this information with your colleagues who aren't able to make it today's session. And I'd just like to say a very quick thank you to our sponsor, Omron Automation and Safety, for making this opportunity possible. Look to Omron Automation and Safety as your partner for world-class machine automation and safeguarding solutions that meet your needs for operator protection and increased productivity. Visit omron247.com to learn more. All right, so now let's dive into the presentation. We're all here to learn about testing e-stop systems, but what do we really know about them in the first place? Most machinery is equipped with an emergency stop, but unlike the automatic guarding systems on those machines, the emergency stop system is rarely used. Large machines and assembly systems may have tens of emergency stop devices scattered over a large area. These devices can fail in ways that can't be easily detected by automatic diagnostics, if present. Many older machines have no automatic diagnostic functions, making the situation even worse. And when these systems fail unexpectedly, the results can be catastrophic. In the next 40 minutes or so, we'll walk through some of the basics of emergency stop functions, the fundamentals of risk and functional safety as it relates to the application of e-stop systems, and we're also going to take a look at some testing requirements. Now at this time, I'd like to formally introduce our speaker for today, Doug Nix of Compliance Insight Consulting. Doug's background spans more than 30 years of engineering technology experience, including product testing, industrial control system design, and machinery safety. Since 1997, he has been studying, applying, and teaching risk assessment principles and processes. Doug also serves on a number of CSA and ISO technical committees and is a frequent contributor of our machine safety column. Welcome, Doug.
Thanks, Lisa. It's great to be here with you guys today. I just wanted to reiterate the comment that you made earlier about the slides being made available. I put together a pretty detailed set of handout notes for people, and so those, I understand, will be made available with the archive, right?
That's correct.
Okay. So for anybody that's looking for a little bit of a deeper dive, you'll find a lot more helpful information in those handout notes when you get them. So as you said, I've been doing this work for roughly 30 years, and I've seen a lot of different types of things. We've come a long way, especially in the last few years, and so I'm hoping to share some of that stuff with you guys today, and hopefully everybody will get a good feel for the direction we're going. I'm going to open up first with a poll, and I want actually to get a chance to find out how many people that are in the audience with us today have actually had a need to test their e-stops, either because they've had a labor inspector in who's required them to do this, or they've had some type of a shop floor incident or something that's generated a requirement. So I'm just going to open up a poll here. It's pretty short, and we'll see what the audience thinks about this particular question. So you've got that up on your screen now. If you can take a second and just respond to that poll, that'd be great. Got lots of people in the poll right now. Getting close to half have actually voted. Almost 75%, good stuff. Looks like the trend is mostly towards never and occasionally. Those two are neck and neck at the moment. We'll see where we come out. Almost 90% now. A couple more people who either don't want to tell us or are thinking about this a little bit longer. A couple more people signing in now. That's all good. Okay, just a few more to go. So based on what I'm seeing right now, I'm going to actually close the poll out, I think, and we'll share those results. So looking at what we've got, it looks like the occasional committee is the group that have won out in this particular poll. About roughly 38% of our folks have had to test occasionally. So it's going to be interesting to see what you think as we go through the rest of the presentation. All right, just hide those results. Okay, well, in order to properly tell this story, I need to take people back to the dawn of the Industrial Revolution in England and talk a little bit about where the whole idea of emergency stop originally came from. If you've ever been in an antique machine shop or a machinery museum, you may have seen something that looks like this. This is an old single-cylinder gasoline engine. A lot of factories at the beginning of the Industrial Revolution were powered by a single central power plant. And that was because these larger power plants were expensive to build and complicated to run. They weren't always gas motors like this. They might have been steam engines or water wheels. But in any case, plants only had a single power source. And in this particular picture, if you look at the extreme right side of the image there, you can see sort of a beige band going vertically up the side. That's actually the main drive belt that feeds the rest of this particular plant. By the way, this engine is actually in operation in an antique machine shop in the United States. So that drive belt then runs up to a series of line shafts that are mounted up in the eaves of the building. And every place you have a machine, you've got a pulley on that line shaft, and you've got a belt that drops off it down to that particular piece of equipment. And you can see, looking at this picture, that gets pretty complicated in a big hurry. The other thing to keep in mind here is that once you start work in the morning, that gasoline engine is running continuously. Those shafts are turning continuously. You can't shut it off, because if you shut that off, you shut the whole plant off. And once we get down to the actual point of use, this is actually a pretty typical horizontal milling machine. This machine was built in the late 1890s, probably. And you can see the drive belts dropping into the back of that thing. So if you consider the concept of emergency stop, and you recognize here that you can't stop the main power plant in the factory, you can't stop the line shafts, how do you stop the machine if somebody gets entangled in that thing? You've got a big problem. Starting and stopping the machines was done with an overhead lever that moved the belt from pulley to pulley. Not a particularly quick thing to do, and not something that would be easily done if you're in a panic situation, and certainly not done from the operator's position. So basically, there's just no way to quickly stop the machine, and there had to be a way developed and for people to be able to do that. So let's talk a little bit about what emergency stop actually is. It's not typically quite as simple as people want to make it out to be in the first place. If we look at the emergency stop function over time, you get a graph that looks something like this, and this actually comes out of ISO 13850, which is the international standard for emergency stop. So at the beginning of the graph on the left side, we're basically in normal operation. The equipment's doing what it's supposed to be. We haven't had a problem yet. We're making parts. Everybody's happy. And at some point, some issue comes up that's recognized by the operator. Now, keep in mind that emergency stop is a manually triggered system. So this is not an automatic safeguard. This requires a person to actually recognize that there's an issue and take action. So the problem's identified, and then sometime after that, the emergency stop is pushed, and that could be quarter second, a second. Sadly, in some cases that I've been involved with, it's been a few minutes before people figure that out. And the machine begins to come to a stop. And the stop occurs sometime later, and that stopping time is based on how quickly the machine can physically stop. So when we get down to the bottom and the machine is stopped now, the equipment is hopefully is in a safe state. And as long as the machinery hasn't been damaged by whatever the issue was, then in theory it can be restarted once whatever the precipitating event was is dealt with. So that's basically how the function works over time. So really, why do we need to test this? It's a pretty simple system, at least it would appear to be, and the real question then is, what kinds of issues come up? Depending on the design of the control system, you can have component failures that get in the way. You can have assembly errors that create problems. I've opened junction boxes on machines and found the contact blocks for the emergency stop buttons hanging in space because the vibration of the machine caused them to fall off the back of the device. There's lots of other types of failures. And in older machinery, you won't have automatic diagnostics in a system, so there's no way for the machine itself to know that its emergency stop system works or not. So the reason to test then basically is to ensure that the system that you've got is at least going to work as well as it's designed to work when you need it. Another question I often get is there any legal requirement for us to have an emergency stop? In Canada, there's no legal requirement in any of the jurisdictions that I'm aware of that would mandate the application of an emergency stop. If you look at the Ontario regulations, like Ontario Reg 851, the only requirements for an emergency stop in the regulation is that if there is one, that it be properly marked and that it be within reach of the operator. So there's no requirement there that says that you must have one. If you look at the Canadian Machinery Safety Standards at 432, you'll find that there is a requirement that says that you should do a risk assessment and have an emergency stop if it has a purpose, if it can actually reduce or limit harm in some way. And there is a conflict in that document that confuses a lot of people. It's actually an error in the text. There's a section that deals with portable control panels that says that you have to have an emergency stop on a portable control panel, and a lot of people take that to imply that all control panels must have an emergency stop, and that in fact is not true. So that sort of brings us around to this question of how then do you determine if you need an e-stop. And I think just before I move on to that, I'm going to say that there are some jurisdictions around the world where they do say that every machine must have an e-stop. And that is also, in my opinion, an error on the legislators' parts, because there are some types of machines where an emergency stop has no point. There is no way by shutting off power that you can actually reduce or limit the harm. And so therefore that emergency stop button is basically window dressing and nothing more. Okay, so let's talk about how we actually figure out if we need an e-stop. What I'm going to do before I move into the section on risk assessment here is run another short poll, and I'd like to find out how many people in our audience actually use risk assessment techniques. And I'm not looking for a specific kind. I just want to know if you use any type of risk assessment in doing machinery design. So that poll's open. Oh, you guys are making my heart smile. This is good. We've got almost, well, it looks like 65% of the respondents so far saying yes. That's fantastic. And it looks like we're slowing down here. A few more people might want to answer. Okay, well, the reason I say this is making my heart smile is that as someone who studies and teaches and applies risk assessment all the time, I unfortunately am called into a lot of plants where they don't know what risk assessment is. And so to see as broad a group as we have online today with us saying that, you know, over 60% use risk assessment, that is a fantastic answer. Good stuff. Well, I'm going to close that poll. I'll just share those results so you can see. So there's only a few people that have never done it. 15%, and hopefully by the end of the presentation today, you'll be feeling like maybe you should be looking into doing that sort of thing. All right. So let's just move back in and talk a little bit about risk assessment. So for the folks that are not too familiar with what risk assessment is about, risk basically is made up of 4 fundamental elements. Okay. The first and most obvious one is severity of injury. And in some jurisdictions, they talk about hazard analysis. If you're talking about hazard analysis, this is the only part of risk that you're actually thinking about. You're only looking at characterizing the hazard itself from the perspective of determining how much damage you're going to do to somebody that's exposed. So if you fail to look at the other risk parameters, you're in a situation where you really haven't fully understood what's going on, and you're going to miss some important stuff. The first of the probability parameters I want to talk about is the probability of the hazardous event. And that basically is the probability of someone actually being injured, considering that they're in proximity to the hazard. So if you imagine for a second a punch press that has no guarding, and you have someone standing next to the punch press, in theory they could stand there all day and never be hurt. So the probability of them being injured really has a lot to do with what they're actually being asked to do. If their job is to stand next to the press all day, then they'll probably never get hurt. But if they have to actually feed material or do other things, then there may be some circumstances that would allow them to be injured. So this is a really important parameter, because not only is it important during normal operation, but without this parameter, you can't deal with maintenance or service modes or any of the sort of unusual or non-routine type activities that need to be done with a piece of equipment and that only occur infrequently. And there are some risk tools out there that don't even include this particular parameter. So this is something you really need to watch out for. The second parameter is frequency and duration of exposure. And some standards mix this up, and they consider frequency and duration to be the same thing. In my opinion, that's also an error. Frequency has to do with how often you're asking somebody to do it, and the duration is typically applied more for, again, non-routine, non-repetitive type events. But when we look at it from the perspective of some of the IEC standards, as an example, that duration factor might be, say, frequent activities might also be activities that are under 10 minutes in duration, and infrequent or long duration activities might be things that are over 10 minutes in duration. So it's important to keep the frequency and the time elements of that particular parameter separate. And then the last one is the potential to avoid or limit harm. And this is where complementary protective measures come in. Emergency stop is classed as a complementary protective measure, and I'll talk about that in some more detail as we go on. So those basically then are the three probability parameters, and your risk assessment tools should directly address all of those. And altogether, then that makes up risk. Okay, so that's in a fairly simple way. That's the key parameters that we need to think about. Alyssa?
So we do have a question that came in a little while ago. So the question is there a time limit in that the machine has to stop once the emergency stop is pressed?
That's a good one. In theory, you need to stop the machine as quickly as you can, even if it results in damage. However, there are very few designers and very few machine owners that want to have their machines destroyed every time somebody hits an e-stop. So the practical approach to this is to say that you need to bring the machine to a halt as quickly as you reasonably can in a graceful way. But if the emergency stop system fails in some way, the system still has to shut down. And if that results in damage to the machine, then it results in damage to the machine. Because it's far more important to limit harm to the person, because you can fix the machine with money, but you can't put a person's hand back on their arm. So, as a machine designer, you need to look at using maximum deceleration rates in motor drives. If you're going to apply mechanical braking, you need brakes that can exert enough force under dynamic conditions to bring things to a halt in the shortest possible time without destroying the machine, if possible. So that's really the short answer to that question. We could talk about that a lot more if there was more interest. So if we go from thinking about the risk parameters in the barrel diagram that I just showed you and just express it as a simple mathematical formula, basically risk R is a function of severity and probability. Okay, and if we break that probability parameter out a little bit more, we can say probability is a function of PR, which is the probability of the hazardous event, FR, which is the frequency and duration of exposure, and AV, which is the probability to avoid or limit harm. Okay. So for the math folks in the room, that gives you basically, in a nutshell, what we're going to do with it. It doesn't tell you how we're going to relate those parameters, and I'm going to show you some scoring tools that actually sort of touch on some different ways you can apply those different algorithms that you can apply those same parameters. So here's one particular tool. This is a new one that's just being talked about. It hasn't been used too much as yet. This one bases the probability of injury classes on individual scales for PR, FR, and AV, and brings those together using the algorithm at the top. You can see that square brackets PR times parens FR plus AV. So that's the algorithm that's being used for the probability class. Those scales, which we're going to look at in more detail, are actually come directly out of the IEC 62061 functional safety standard. So there's some other kind of cool advantages to this. And then based on how you rank the severity and what probability class you assign to things, then that drops you into some approximate bins. And I want to point out a typo on the risk range portion of this slide. You'll notice that the low range goes from 11 to 20 and the moderate range goes from 30 to 100. And that's not because we don't think about risks that fall between 20 and 30. It's because there's a typo and the moderate range should actually go down to 20. So when you get your notes, you might want to mark that up and just mark up that the moderate range goes down to 20, not down to 30. Okay. So here are is the severity class. As I mentioned, this comes from 62061. And, you know, with 4 divisions in the scale, we've got some fairly good granularity here. We can basically subdivide our types of injuries reasonably well. We've got a probability of occurrence of the hazardous event scale that looks like this. Goes from 5 down to 1. And that little asterisk on the very high portion of the scale is important. We've got a note in here? No, we don't. The asterisk tells you that if the probability of the hazardous event is related to the normal operation of the machine, so we're in normal operating mode and the hazard is created by the normal motion of the machine, then you have to rank the PR factor at 5, okay, because that is the normal operating circumstance for the machine. So the probability of occurrence of that hazardous motion is 100% if the machine's working, so it has to be ranked as a high. If this is a situation where you're looking at a maintenance activity or some other situation where this is not due to the normal operation of the machine, then you can pick from 4 down to 1. Okay, and when you're using a scale like this, it's important to document the reasons you have for not using the highest classification. Okay, because you may need to justify that in the future. So it's good to keep those assumptions close at hand. If we look at the frequency and duration of exposure scale, this is broken up fairly nicely. Some of the tools that are out there only use 2 factors or 2 divisions in each of their scales, and unfortunately that makes it extremely difficult to accurately score things. And some of them even have large gaps in the middle of the scale, which actually prevent you from dealing with things that happen you know, less than once an hour, let's say, but more often than once per day. So when you have a scale like this, then you have an opportunity to score things a little bit more along the lines of what's really going on in your plant. And as you can see, it goes down from 5 down to 2. And the fact that the first 2 levels are both 5 is correct. Basically, we're scoring the frequency of exposure high as anything that happens really more than once per day. And then the last scale in here is the possibility of avoiding or limiting harm, and so this basically goes from 5 down to 1. And really, if you were working with this scale and you wanted to have a 2 and a 4 in your scale, you could certainly add in a couple more definitions for those point numbers if you wanted to. In my experience, I don't think you really need them, but if it makes you happy, there's certainly no harm done. Okay, so when we put those all together then, you've got the full algorithm up there at the top of the screen. So risk is combined as a combination of the severity of injury times the probability factors, and that's probability of hazardous event times the sum of the frequency and avoidance. And this is actually pretty important because In this circumstance, if the probability of the hazardous event is quite low, even if the frequency and avoidability figures give you a fairly high number in the curve parenthesis, you end up with a low probability score. And that's really important because you don't want a situation where you're ranking a low probability event higher than it should be in your scale. So that's why that's done the way it's done. If you look at the originating material in 62061 from where this comes, what you'll find is that in looking at it from a functional safety standpoint, they add those parameters together, and they do that for a different reason. Okay, so when we substitute in these example values I've given you here, you end up with a risk score around 120.
So I'm just going to jump in here with a quick question. So Doug, can you please mention the name of the suggested risk assessment again?
I didn't give that name out. It's actually one that I created in a paper that is not yet published, and which unfortunately I can't yet share with anyone. But it's been developed as part of a project I'm working on to develop means of facilitating linking risk assessment and functional safety, which is a big problem at the moment. And so that tool is actually mine. When you get the handout notes, you'll find there's a reference list at the end, and I do actually reference the name of the paper there. And hopefully by the middle of July, I'll be able to make that publicly available. So just keep my email handy, and somewhere after the 15th of July, pop me an email and I'll send you a copy of the paper. Okay, so we got one more poll to run here. And I need to know from people which parameter they think is actually affected by emergency stop. So let's go to that poll. I'll get that launched. And if people can just take a quick sec and answer that, that'd be great. I know I blew through the risk assessment methodology pretty quickly, so we'll see what people think. We have a good group online with us today. Smart people. A little more than 60% of people have responded now. Slowing down a little bit. Come on, don't be shy. There's no bad answer here. And we're over 75%. Give it a couple more seconds here for people to finish up. Over 80. Come on, there's a few more people out there that must have a thought. All right, looks like people have pretty much finished answering. I'll close that and share it with people. Okay, so 58% of you have the correct answer. The probability or the possibility to avoid or limit harm, or the AV factor, is actually the one which is affected by this. The severity of injury, when you're scoring severity of injury, unless the control measure that you put in place physically changes the characteristic of the hazard in some way, you cannot reduce the severity of injury. So dependent on how the system works, you know, if we're talking about, say, shutting off a laser beam, then I might agree with you that you could reduce the severity of injury. But if we're talking about a large rotating high inertia thing that's going to coast for a bit, then it's a much more questionable thing about whether you could reduce that. And again, remember, this is not an automatic system. This is a situation where somebody's already in trouble. You're going to push the emergency stop button, then you're going to dial 911 and wait for the ambulance to come. So chances are that limiting the severity of injury is going to be the marginal part of the change that you're going to do. Okay. All right. So let's go back to our presentation here, and we can talk a little bit more about that. Okay. Having an issue moving back. We've gone off air. There we go. Okay, we're back. Sorry about that. Minor technical glitch. Okay, so the correct answer was that emergency stop affects only AV, or the possibility of avoiding or limiting harm. All right. So if we look at how that works then, using the same basic algorithm, if I use the same example score values, we would in this case, or I would suggest anyway, that you would drop the AV factor from a 5, or a 3 rather, down to a 1. Okay, so that's actually how you get the reduction in the factor, and when we look at how that calculates, you go from 120 down to a 60. So that's a pretty good risk reduction. You're not into the situation where I would say no other control measures might be required, but it's still a pretty good result at the end of the day. All right. So any questions on that? Looks like we're good. Okay. All right. Let's move on. So we need then to talk about risk reduction and how we actually look at that. So in terms of the risk reduction, I mentioned that we go from 120 down to a 60. So clearly we've managed to achieve some risk reduction in the process. And if you look at what that's done actually to where we come out in the binning group, we move actually from up in the high range down into the moderate range. So it's clear, and it should be clear in your documentation when you look at the risk assessment and that justifies having an emergency stop, that this is what you expect to have happen. Okay. All right. So the other thing that comes up commonly when we're talking about stop is stop categories, and these are not the functional safety architectural categories B1 to 4. That's not what we're talking about. What we're talking about is the stopping categories that are defined in IEC 60204-1 and in NFPA 79. And those two standards are referenced in the reference list if you're not familiar with them already. So basically there's 3 categories of stopping effect or stopping actions that are categorized. Category 0 stops are removal of power. That's just the same as pulling the plug. Category 1 stops are a controlled stop where you reduce the speed or the operation of the machine down to a stop condition, and then you drop power. In both cases, both methods end in a category 0. So you start in a category 0. In a category 1 type stop, you start by controlled action on the tooling, and then you remove power at the end, which is in the end a category 0. And the third type is category 2, which is a controlled stop where you then maintain power to keep control of the tooling. Only category 0 and 1 are permitted for emergency stop. So even though the category 2 exists, it can only be used as part of the process operation of the equipment and not as an emergency stop function. So that one and not that one. Okay. The other thing to keep in mind is that these stopping categories can be used for any kind of stop. They're not exclusively limited to emergency stop. So when you're thinking about the normal stopping action of your machine, then these stop categories also apply. Okay. Any questions so far? It doesn't look like we've had anything new come in. All right, let's talk a little bit about functional safety requirements. Oh, we do
Actually, Doug, right before we begin, we just got another question asking, can category 2 be used with STO?
Well, safe torque off is intended for use in emergency stop and also for gate interlocking. And category 2 stops, if they're used as part of the process control, can certainly affect STO. But if we're talking about the design of emergency stop, which is what we're talking about today, the answer is no, you can't. So really it's a question of what are you trying to do with the drive and what specifically is your application. And if you're using STO because you intend it to be part of your safety function, then category 2 stop functions are out. Okay, hope that answers the question. All right, let's talk about functional safety a little bit. So how reliable does a system need to be? This is a huge question, and it's one that's commonly asked. And it's not really the easiest question to answer. But we do have some tools available to us. One of the things that we need to think about in terms of reliability is what they call the bathtub curve. And basically what we're looking at in the bathtub curve is the typical kind of failure behavior that we see in any kind of product. Doesn't matter what it is. So on the left side of the graph, we basically got the infant mortality. These are our products which fail before they leave the factory. They fail either in production tests, or they fail for QC requirements, or they fail maybe during a burn-in test or some other pre-sale type testing. You get down into the flat lower portion of the curve, and that's the normal life. And the normal life of a piece of machinery is really important, particularly when we talk about functional safety. And eventually, at some point downstream, we get to a place where the failure rates start to increase, and that's because the components are wearing out, and we're now into the end-of-life wear-out portion of the curve. So this entire concept of functional safety and reliability is all underpinned by this concept that's shown in the bathtub curve. Go ahead, Alyssa. Okay. So if we look at the graph here, I've just added the TM vector to this. Those two bars basically represent the normal life of the machine, and in the standards they actually call that the mission time of the machine. And that mission time, or TM, is actually defined in the standards as 20 years. Okay, so all of the functional safety calculations that you do, whether you're doing them under 13849 or 62061, all of those are driven by this 20-year lifetime. If your machine is designed to live less than 20 years, then that may affect your reliability calculations, and it will definitely affect it if you're looking at a lifetime that's predicted to be longer than that. The 20-year time frame doesn't have a particularly scientific basis. It basically came about because people that are involved with control system design looked at the average lifetime of electrical control systems and said, 20 years is about it, and at which point you're going to have trouble getting parts and so on for an older system, and so at that point you're probably rebuilding or replacing the controls if the machine is still in service. So that's where that 20-year lifetime came from, and it does, in this case, TM is actually taken from 13849 if you're interested in looking that up.
So before we carry on to the next slide, there is a comment that came in, and this attendee said, with a robot, if you're using category 0 to 1, there is a possibility of the robot dropping what he's holding, thereby causing a danger.
But you're misinterpreting. When I talk about a category 0 or category 1 stop, I'm not talking about releasing power from the grippers. What I'm talking about is stop of motion. So if the robot already has a grasp on a part, there is no motion if we only look at the gripper, but the relative between the gripper and the part. What we're talking about is the physical motion of the robot itself. So, one of the items that has to be assessed as part of your risk analysis is what is the hazard related to dropping a part. There may be personnel hazards, or there may not. It may only be a loss of product type hazard. You need to assess that carefully and look at it. But fundamentally, what I'm talking about is stop of hazardous motion or stop of hazardous energy. And typically, if you were to release the robot gripper in mid-flight, then you create a new hazard, which is a flying part, and you definitely don't want that. So I'm not suggesting you should do that. All right. So this is the Annex A so-called risk graph out of ISO 13849. You cannot use it for analyzing risk. It is only for selecting a performance level requirement that you can then analyze your control system design to. But it uses the same basic factors that are used in other risk assessment tools. So we have a severity factor, S1 and S2. We have a frequency and duration factor, F1 and F2. And we have a probability of avoidance factor, P1 and P2. Okay. In this particular case, the probability of the hazardous event parameter is missing. And the reason for that is that they're assuming that if you are using an electrical control system as part of the risk mitigation, that the probability of the hazardous event is 1 because the machine is in operation. So the selection of the performance level here has absolutely nothing to do with conditions where that safeguarding system may be offline for maintenance or other reasons. Okay, so that's why you see that parameter is missing. So if you need to make a note on this particular slide, what I would say is note that PR equals 1 or 100% in this particular case. Okay, So we can actually rank each risk using this particular tool. In this case, I'm going to suggest we're going to pick an S2 because we're now talking about how you figure out whether at what level of reliability is required for an e-stop. You need to make some assumptions about how much damage is going to be done and why you're pushing the button. So I'm going to assume that in any situation that's going to require or where you might expect an operator to push e-stop, we're likely to have an S2 type of injury. So that's anything more than basic first aid. Okay? The process is out of control in some way. Our frequency is going to be infrequent. One would hope that your process is only rarely out of control, and so we'll say it's an F1. It's possible in some circumstances to avoid or limit harm because you can perceive the situation and hopefully stay out of its way. So if we look at it from that perspective and we score it using the risk graph, we come out to PLC. And PLC is pretty interesting for a number of reasons. The new edition of ISO 13850, which is the international emergency stop standard, when it's published, and it should be published, I would think, anytime this summer, will actually make a requirement that all emergency stop systems meet at least PLC. So they're making the same basic assumption that I've just showed you. And PLC can actually be done with single-channel architectures, with single-channel monitor type architectures, or with Category 3 type dual-channel cross-monitored architectures. Any of those will work. So by using the performance level, we actually have a lot of flexibility in what types of systems we use. So we go back and look at how that actually scores. You can see we start out at 1, we score a 2, an S2, an F1, and a P1, and that takes us all the way over to a PLC. Okay.
So we have another question that came in. And this one's asking, is it really necessary to use this method to evaluate all operations? Or can we just can we define the risk only to have an accident?
The technically correct answer is that you need to conduct a risk assessment on machinery designs and on machines in your shop. If you look at Z432, there's a requirement in Z432 that you carry out a risk assessment on machines. If you look at Z1002, which is the CSA Occupational Health and Safety Risk Assessment, it says thou shalt do a risk assessment in all cases. If you look at ISO 12100, the international mother standard for machinery safety, it says thou shalt do a risk assessment. So the best answer I can give you is thou shalt do a risk assessment. If you choose not to do that, if you don't do a detailed look at what's going on with your equipment, you're going to miss stuff. And the things you miss are the things that will bite your people. So I can't emphasize that enough. Okay, so we've come to the conclusion we need at least PLC. Let's look at what that means in terms of the system design. If you're interested in using the IEC standard, which is the 62061, it talks about safety integrity levels, or SILs. And 13849 gives us this nice little table that allows us to directly map from PLs to SILs. So in our last example, we came out with a PLC. You can map that to a SIL 1. If the risk levels that you're trying to control with your emergency stop are different, then you will end up with a higher level PL and therefore also a higher order of SIL. Okay. So within 13849, we have this great little chart. This is actually figure 5, and it actually illustrates all the key points within 13849. Really, all the ideas in that entire standard are in this diagram. So we have bands that run vertically that show the different categories of architecture. Those are the physical hardware categories that we're talking about. Those bands are broken up into 3 different sets of shadings for different failure rates. So we've got the MTTFD, which stands for mean time to dangerous failure, and that's broken up into low, medium, and high. And then we also have some diagnostic coverage that's shown along the bottom. And the performance levels are shown on the left-hand vertical axis. So if we look at PLC, then you can see it spans this center portion of the chart. And what this tells you, if you look at it, is that if you choose to use a single-channel architecture, which would be a Category 1, with no diagnostics, then you need very high-quality components with very low failure rates in order to meet the MTTFD high requirement. That's why that band is black. If we move into category 2, which is a single channel but with some diagnostics built into it, then we have an opportunity to move some of those components down into a medium level of MTTFD, and so on. If we go up, if the diagnostics get better, we go into a DC average of medium, then we can use, again, slightly lower quality components. And finally, if we go to a dual channel cross-monitor type of hardware architecture in category 3 with a low level of diagnostics, now we can abandon the very high quality, low failure rate components. And finally, once we get diagnostics up to a medium level, which would mean that we're diagnosing in excess of 75% of the possible faults in the system, now we can actually move to an MTTFD of low in the channels. So that's really what that table tells you, and it shows you quite neatly how you can use the different architectures and the different levels of diagnostics and component qualities in order to come out to the same result. Because PLC across the board will have the same kinds of failure rates regardless of which one of these particular bands you choose to use. Okay? So if we look at category 1 and 2 architectures, category 1 is pretty straightforward. It's a single channel. Category 1 is different from category B in that the components are what they call well tried. And that's a whole other discussion that we could get into. But well-tried components do include safety components that are rated for safety applications by their manufacturers. So if you buy a safety switch that says it's intended for use as an interlocking device, and the manufacturer tells you that, then that can be considered to be a well-tried component. Okay. You'll see there's no testing in here. We basically have no feedback between the different logic blocks. We move into category 2. Now we have some test equipment. Still the main channel, I, L, and O is single, but you can see there's now some monitoring going on by the test equipment, which is that TE block, and it's looking at whether the input device, the logic block, and the output device are doing their job. Typically, in a category 2, you can still have a single component failure cause the loss of the safety function, but you are able to detect some types of failures. Okay, so that just depends on the design of the system. We don't see category 2 used very much, but it is possible to do it. And much more commonly, we see category 3, which looks like this. Now we have 2 completely independent channels, I1, L1, O1, and I2, L2, O2. And there's cross-monitoring, which means the two channels are basically watching each other to make sure that they're in agreement all the time. There's no input device monitoring in category 3, so there is a requirement that, for instance, on an interlock door, that you have 2 switches, 2 independent switches on the door. These are mechanically separate, independent devices, not a dual channel and a single switch. Okay, and there is monitoring of the output devices, so the output contactors or control valves will have some feedback into the logic blocks. So that's basically the difference in those 3 structures from a logical standpoint. These are clearly not schematics, but they show you, from a functional standpoint, how things work. So the testing requirements basically are driven by the architecture, and if we look at category 1, there's no testing because basically there's nothing built into the architecture. So that means that if you want to test, you're going to have to determine how you want to test and when you want to test. There's no internal diagnostics. Category 2 has some requirements on testing. There's a basic requirement in the standard that you have at least 100 times demand rate for tests, and what that means is if your emergency stop is used twice a day, then the expectation would be that the system would automatically test that system 200 times per day. And there's also a requirement in there that the MTTFD of the test equipment is at least twice that of the logic block. So that's some fairly strenuous requirements on the on category 2 components. In category 3, it tests every time the system has a demand on it. So every time you push the button or every time you open an interlock door, then the system tests itself to make sure that it's functioning properly. Most safety relays and safety PLCs are actually testing hundreds of times per minute, looking for shorts and opens and unintentional grounds and all kinds of other goodies. So if you're using safety rated components like that, you're probably in the clear. If you have an old system, then you're in a situation where you may not have any testing and you may have to figure that out on your own. The other thing that comes into this discussion is proof testing, and I'm going to try and wrap up here as quickly as I can in case we have any other questions that need a little bit more time. Proof testing is basically what happens first at the factory. So in the standards, the requirement is that a proof test happens at least once in 20 years. And that proof test is a detailed functional test of the systems to make sure that they work appropriately. You can have more proof tests. And if you add proof tests, for instance, at the end of a maintenance cycle or something like that, then you can actually improve the reliability of your system, because the definition of proof testing is that you're evaluating the system to make sure that it works as designed when it was new. So if you do major maintenance, you do some repairs, something like that, you should really conduct a full proof test to make sure that that critical system works appropriately. And there's a lot more information available on proof testing. It would take me another hour to explain it in any great detail. Okay, so one last poll, and then I think we're just about done. I want to find out how many people here were aware of functional safety before this webinar today. So I'll just launch that poll quickly. Oh, this is looking good. Over 80% so far. A few more people to answer the poll. All right, looks like we're going to be sticking somewhere around 83%. So I'll just share those results with you. So this is really good news to me, because functional safety is an area that confuses a lot of people. There's a lot of misunderstanding with machinery engineers and controls engineers, and unfortunately even with a lot of safety professionals, about what functional safety is about. It's a growing area of concern, and it's something that if you're not really familiar with it and you're involved in machine design, you need to understand. So I'll hide those results, and we'll finish up the last couple of slides here. All right, so the good news in all of this is if you've got systems that have safety relays and safety PLCs in them, your test requirements are probably already covered. It's a very high probability that they're already covered. The bad news in all of this is that if you don't have that, and you have systems that might look, something like this. This is, early 90s, maybe early 80s type of e-stop systems. You have a problem, because you have no testing built in, you have no diagnostics built in, and my best bet would be that most older systems that have e-stops that look like this probably only meet Category B requirements, and so you're not going to come anywhere close to hitting that magic PLC mark. So if you have a system that looks like this, you need to spend some time to do some functional safety calculations and determine what you're actually dealing with before you try to make any assumptions about what you need to do for tests. As far as more good news is concerned, it's actually pretty easy to correct old systems like that. You can swap out an old MCR circuit like that with safety relays pretty quickly and pretty inexpensively these days. And so at the end of the day, you can probably solve that problem pretty quickly and pretty easily. And I'm sure the folks at Omron would be more than happy to hear from you and help you out with that. When we're talking about proof testing and really looking at manual tests, we have one more piece of guidance that can help us out, and this comes out of the interlocking devices standard, ISO 14119, and it says that if we're looking at interlock systems that are PLE, we should be looking at testing somewhere on the order of once a month. So PLE is very high reliability. And if we're looking at PLD type systems with Category 3 architecture, we might be looking at tests on the order of once every 12 months. So most industrial control systems, unless you're talking about injection molding machines or punch presses and that type of thing, most systems will probably be Category 3 architectures. And chances are they're going to be somewhere between PLC and PLD. So if you're looking at that kind of a system, probably testing it manually once a year is probably good enough. So that's also good news for everybody out there. 14119 doesn't deal directly with emergency stops, but unfortunately the e-stop standards don't tell us the same information, and so this is the best advice that I can give you based on what's in the standards today. Okay, well, we have only about 5 minutes left for any additional questions. But perhaps if there are some, Alyssa?
There's actually a really good question that just came in. So as a machine user, how do you get machine manufacturers to accept and understand and provide machines that are compliant to 13849 type functional safety requirements, because many play dumb.
Mm-hmm. Well, and in fact, in many cases, they're not even playing dumb. They actually are dumb.
Oh, boy.
sad to say. And, you know, not to speak ill of small and medium enterprises, because a lot of those people are my clients. The reality is that there are an awful lot of control system designers out there that have never been exposed to this stuff. The place I would start in enforcing it is actually in the purchase agreement. There should be some explicit requirements in the purchase agreement that says that system has to meet certain minimum requirements. And ultimately, if you don't require that a risk assessment is done by the machine manufacturer, you've missed the boat to begin with. So you may want to put that in your documentation. You may have difficulties getting machine builders to give you their risk assessments, and that's actually not unreasonable on their part, because they may have proprietary information that they don't want to share. But they should be willing to share a list of residual risks that comes out of their risk assessment. And all the safety functions that are on their equipment should be driven by safety requirement specifications that are driven by the risk assessment. So there should be documentation that shows explicitly why they chose what safety functions they had. So if you put in your purchase requirements that the system has to be based on current functional safety standards, I wouldn't sit too heavily on either 13849 or 62061. I think you need to be able to give the machine builder the option to use either or both as appropriate, but they need to actually show evidence that they've done that work. And they should also be able to show you evidence that they've done a risk assessment, even if they don't share the actual risk assessment document with you. Okay, another question just came in. What training system do you recommend for further information on machine safety design? And how do you feel about CMSE certification? CMSE, so you're talking about the Certified Machinery Safety Engineer certifications. That's actually a fairly new thing, and from the people that I've talked to that have done it, and I'll be quite honest, I've considered getting the CFSE, Certified Functional Safety Engineer, myself. One of the challenges is that the way they're structuring the exams right now is not necessarily reflective of the material that they're teaching, and so it can be extraordinarily difficult to pass the exam. And unfortunately, that's a problem with the pedagogical decisions they're making in developing that training material, and that's an issue. Unfortunately, that's not one we can fix. I think that somebody that has a CFSE or a CMSE certainly has some demonstrated credentials, but it's pretty early in the life of those credentials to know how much value they're going to have. So if you like having extra letters after your name and you have some spare money and time and you want to throw it at it, I don't see why you shouldn't do that. But at this point, I'm not aware of any legal requirement anywhere that would force you to do that. So I think time will tell. All right, next question. When testing e-stop circuitry, do you test each and every e-stop device, or is it just acceptable to test a single or random device to ensure system operation? I would say every device is the best choice, followed by the ones that get used the least. The ones that are used all the time basically get tested every time they're used. So, you know, you don't really need to worry about additional explicit testing on those. But if you've got an e-stop that's located at the back of a warehouse near a gate that's almost never used, I would definitely be testing that sucker to make sure that it hasn't developed some failure mode that you're not capable of diagnosing. Okay, so we're going to take our last question here. Are there any requirements that lead us to a required frequency for manual testing of e-stop systems? Well, the only one that that I have been able to find is the one I showed you from ISO 14119, and that's in the interlock standard. So it's not explicit for e-stops, but it is the best technical advice available at the moment, and that is at least once a month for PLE Category 4 systems, and at least once a year for PLD Category 3 systems. There's no other more explicit information for, say, you know, Category 2 PLC or anything like that, so you'd have to make a judgment call on those. Okay, so we're just about to wrap up here because we're running out of time. So some questions are unanswered. We'll get back to you with an email with a explanation. So, all right, just want to thank
Doug for a very informative discussion, and it sounds like we've got some really interactive discussion here happening today. So I really hope everyone got some key takeaways from the session and you found it helpful and useful for you. So as a reminder, the presentation will be archived on our website, and we'll send you an email out next week with a link to download that, and also a PDF with some additional notes.
And my email address and contact information is in the slide deck as well. So please, if you've got some specific questions and you need some help, don't hesitate to give me a call.
Great, thank you, Doug. So just again, thank you to our sponsor, Omron Automation and Safety, for making this educational opportunity possible. And thanks again, everyone, for joining us today.